Titanium is prized for being stronger than steel, yet nearly half the weight, vital for everything from spacecraft to life-saving implants. But behind its silvery surface lies a little-known truth. Making titanium pure enough for the world's most demanding applications requires a secretive, high-security process. And failure can lead to catastrophic flaws or eye-watering costs. In this documentary, we go inside the closed doors of titanium production to uncover the hazardous chemistry, global supply chains, and relentless drive for perfection that shape this extraordinary metal. So how do ordinary rocks become the heart of modern engineering? And why is this transformation so fiercely protected? Hidden beneath red earth and black sands, titanium's journey starts with minerals that look nothing like the gleaming metal they'll become. The most important sources are ilmenite, a dense iron titanium oxide, and rutile, a rare mineral that holds titanium in its purest natural form. Across the globe, Australia leads with nearly 44% of known rutile reserves, while South Africa, Canada, and China operate some of the world's largest open-pit mines. In these remote regions, fleets of excavators and haul trucks carve through layers of sand and rock, stripping away overburden to reach ore deposits that stretch for kilometers. Once extracted, the raw ore is far from ready for high-tech use. Technicians direct the next stage, crushing the rock into fine particles, then guiding it through a maze of separation lines. Magnetic drums spin at high speed, pulling iron-rich grains away from the rest. Gravity tables take over, sorting heavier titanium minerals from lighter waste. Each pass through these machines increases the concentration of titanium dioxide, boosting it from just a few percent in raw ore to over 90% in the final concentrate. In the control rooms above the separation plant, operators monitor every variable: flow rates, drum speeds, particle sizes, knowing that even small mistakes can let valuable titanium slip away. The resulting concentrate, now a fine black or brown sand, is bagged and sealed for shipment. This purified feedstock is the foundation for everything that follows. Only after this careful upgrading is the material ready to enter the chemical heart of titanium production. Inside the chlorination hall, operators oversee a network of insulated pipes and pressurized tanks, where the next transformation unfolds at nearly 900 degrees Celsius. Here, finely concentrated titanium dioxide is fed into a towering fluidized bed reactor, where it floats on a rising stream of hot chlorine gas. Coke, a carbon-rich solid, is added to drive the chemical reaction. As the mixture churns, chlorine strips away the oxygen from titanium dioxide, releasing clouds of carbon dioxide and forming a new compound, titanium tetrachloride. Workers call it tickle, a nod to its chemical shorthand, TiCl4, and its reputation for volatility. Tickle is a colorless, fuming liquid that boils at just 136 degrees Celsius. Even a brief encounter with moisture triggers a violent reaction, releasing dense white clouds of hydrochloric acid and fine titanium oxide dust. That's why every valve, flange, and pipe joint is sealed and double-checked for leaks. The entire reactor is surrounded by containment walls and blast panels, with chlorine detectors and scrubbers on constant alert. In the event of a leak, emergency caustic scrubbers flood the area with neutralizing solution, and operators are trained to evacuate within seconds. The first stream of crude TiCl4 is a cocktail of metal chlorides: iron, vanadium, magnesium, and more. Fractional distillation towers separate these impurities, leaving behind purified tickle ready for the next stage. Each batch is sampled and analyzed in on-site labs, where even trace contaminants are flagged for removal. Only after this volatile liquid passes a battery of tests will it move on to the reduction reactors, where titanium's true metallic form is finally within reach. Inside the reduction hall, the heart of titanium production beats quietly behind armored doors. Here, a lead engineer sits before a wall of monitors, eyes shifting between glowing telemetry graphs and the silent retort. a thick-walled steel vessel braced for both heat and secrecy. The process begins with a precise measure of magnesium loaded into the retort under a shield of argon gas. Every gram is accounted for because too little risks incomplete reaction, while too much can trigger a runaway event. Once sealed, the retort is purged of air. Any trace of oxygen or moisture could spell disaster when titanium tetrachloride is introduced. Heated bands wrap the vessel, driving the temperature steadily upward, climbing past 800 degrees Celsius. Inside, titanium tetrachloride vapor is metered in, its flow controlled by mass flow valves and real-time pressure sensors. The reaction is slow and deliberate, stretching over 2 to 5 days. Magnesium strips the chlorine from the tickle, leaving behind a porous, metallic sponge and a pool of magnesium chloride at the vessel's base. The engineer's hands hover above emergency shutoffs, ready to intervene if a temperature spike or oxygen leak appears on the screen. Throughout the batch, the control room hums with tension. A sudden alarm, a flicker in the oxygen analyzer, and the entire process could be lost. But when the final readings stabilize, the retort is allowed to cool. Only then is the vessel opened, revealing a brittle gray sponge. Titanium in its first true metallic form, still laced with salt and magnesium, not yet ready for the world outside. The magnesium chloride byproduct, far from waste, is siphoned off for recycling, closing the loop in this high-stakes industrial alchemy. Pressed into dense briquettes, the titanium sponge now faces its most unforgiving trial. Inside the melting hall, a chief metallurgist oversees the transformation, eyes fixed on a bank of gauges and monitors. The air is thick with the hum of high-voltage power as rows of vacuum arc furnaces wait to ignite. Each furnace is sealed tight, the atmosphere purged with argon until oxygen drops to near zero. Any stray molecule could ruin the entire batch. Titanium's melting point is 1,668 degrees Celsius, hotter than most metals can withstand. At these temperatures, the slightest contamination turns a future jet engine into scrap. The arc strikes, unleashing a blinding blue-white flare. Briquettes collapse into a molten pool, impurities vaporized and drawn away by the vacuum. Every few minutes, the metallurgist checks readings, pressure, current, gas levels, knowing that a spike in oxygen or nitrogen would mean starting over. As the melt stabilizes, the titanium is poured into massive molds, forming ingots that weigh between 8 and 15 tons each. These ingots are the backbone of aerospace and medical manufacturing, but only if they pass the next hurdle. Before leaving the melting hall, each ingot is scanned from end to end using ultrasonic waves. Technicians listen for the faint echoes that betray hidden voids or cracks, flaws that could spell disaster at 30,000 feet. Only the ingots that pass every test are stamped with their batch code and certified under ASTM and ISO standards. Here, perfection isn't a luxury, it's the minimum requirement for flight. Inside the factory's accounting office, plant managers pore over electricity bills that dwarf those of entire neighborhoods. Every ton of titanium demands as much power as running a small town for a week. Unlike steel, where high-volume output helps cushion costs, titanium's process is slow, wasteful, and unforgiving, losing up to 40% of raw material before a single ingot is poured. That's why titanium routinely costs 10 times more than steel, limiting its reach to only the most demanding applications. Meanwhile, environmental advocates track every shipment of chlorine and every barrel of magnesium chloride waste. Recent years have brought hefty EPA fines for leaks and improper disposal, pushing factories to invest in tighter containment and recycling systems. For both managers and regulators, the challenge is clear. Keep the metal flowing, but keep the risks and waste under control. In research labs just beyond the factory floor, teams of engineers and chemists are chasing breakthroughs that could change titanium forever. The FFC Cambridge process, named for the university where it was invented, uses molten salt electrolysis to turn titanium dioxide directly into pure metal. Early pilot plants report energy savings of up to 50% compared to the traditional Kroll process, with far less hazardous waste. Yet, scaling up remains a challenge. Impurities and cost per kilo are hurdles still under study. Meanwhile, additive manufacturing is rewriting the rules for design. By layering titanium powder with lasers or electron beams, 3D printers can create intricate parts impossible to forge or machine. But fine titanium powder is highly flammable, demanding strict safety protocols to prevent fires. If these innovations reach full production, titanium could move from the realm of jet engines to everyday technology, making the metal as accessible as aluminum. Each year, more than 210,000 tons of titanium sponge are produced worldwide. Yet the core process, the Kroll method, has changed little since it was first documented in Dr. Kroll's wartime notebooks of the 1940s. Today, every ingot must pass ASTM and ISO standards, with inspectors using ultrasonic scans to verify purity down to microscopic levels. Despite detailed technical records and decades of engineering progress, critical details about reactor operations and quality control protocols remain classified by many governments and manufacturers. While the Kroll process delivers titanium strong enough for jet engines and medical implants, it is energy-intensive and costly, keeping titanium prices about 10 times higher than steel. Ongoing research into new methods, like the FFC Cambridge process, is documented in laboratory reports and patent filings, promising lower costs and reduced emissions. For now, the future of titanium relies on perfecting a process that remains, by necessity, both transparent and tightly guarded.